review, today I will present our work on adaptive safe merging control for heterogeneous autonomous vehicles using parametric control balance functions. Talking about self-driving cars, the first concern people have is about safety. So how to ensure safety while finding a better way to model heterogeneous robot interaction? These are the motivations of this work. As for technical objectives, first we have safety as a priority for forming proof guarantees. And secondly, we want to remove the over strict assumptions on surrounding robots to make them really think and act like a human. And thirdly, we want to enhance the safe controller's expressivity for more precise safe behavior characterization. And here's our proposed framework for heterogeneous vehicles, especially in highway merging scenario. It has two major components: behavior prediction and safe controller. The core idea of the safe controller is based on the forward invariance property of the control boundary function. So CBF is providing a way to constrain the robot motion so that the robot will always stay in this defined safe set. And the core idea of our proposed parametric CBF is that we are introducing a new composition of the class K function as a linear combination of higher order polynomials to better characterize the system level safe behaviors while preserving safety guarantees. The design of the safe controller starts from the minimal deviation control as the objective function. And beside the actuation constraint, here's where we have the parametric CBF to account for safety. Comparing to the traditional CBF, the proposed parametric CBF can actually provide richer behavior description thanks for the higher order polynomials. It also has the advantage of computational efficiency thanks for the nature of the linear combination design. And these advantages makes the proposed parametric CBF highly suitable to be applied in more complex systems. And in the module of behavior prediction, rich linear regression is used to enable the prediction of surrounding robots' safe controller parameter based on observations. The first application we show is behavior prediction. The task here is to predict the driving style parameter of the blue car while it's interacting with surrounding heterogeneous robots. And we can see the result here. It reaches convergence with only 10 steps, which means it's quite computationally efficient. And in the second application, the goal here is to show that how this kind of prediction knowledge can contribute towards more efficient safe control. And now it's time for the Eagle robot, which is in orange, to merge with the prediction object, which is in blue. And we can see that the use of prediction actually significantly improves the Eagle vehicle's task efficiency by over 39%.
Jesse, are you in the crowd? Cool. Yeah. All right. Tell me when you're ready.
Yeah.
Go.
Hi, my name is Jesse Jane, and today I'll be presenting my work on safe learning for uncertainty-aware legged locomotion via interval MDP abstraction. This work was done with Professors Ye Zhao and Sam Coogan. So the motivation for our work is the legged robot motion planning problem. Specifically, we consider a scenario in which we have a high-level task for the robot specified using the syntactically close-state fragment of linear temporal logic. However, the robot has partially known dynamics, and additionally, there exists uncertainties in the environment such that the initial probability of satisfying the specification is too low. Then the goal of our work is to find safe paths in the state space which the robot can travel to sample and learn the uncertainties in the system, thereby improving the probability of satisfying the specification. So the methodology of our work is to assume a hyperrectangular partition of the state space. Using this partition, we can then construct an interval Markov decision process abstraction of the system dynamics, which formally incorporates the uncertainties present in the system and respects the inverted pendulum model dynamics of the legged robot. We then combine this IMTP abstraction with a finite state automaton of our specification to create a product IMTP construction. Using this product IMTP construction along with graph theoretic methods, we can then calculate safe paths in the environment which don't violate the specification, allowing the robot to sample the uncertainties in the system. We use Gaussian process regression with these samples to learn separately the terrain and model uncertainties present in our system, and then feed back our GP model into the product IMTP, shrinking the transition probability intervals and thereby iteratively improving the probability of satisfying the specification. So we demonstrate our work with 2 case studies. In the first case study on the left, the goal of the robot is to avoid the red hazard states while reaching green goal state in the presence of unknown terrain as well as partially known system dynamics. And in the case study on the right, the robot needs to accomplish the same task while additionally returning to the orange charging areas every few steps. In both cases, we demonstrate that the robot is able to safely wander around in the environment without violating the specification, learning the uncertainties in the system until it is able to achieve sufficient probability of satisfying the specification. So I'd be happy to take any questions you have during the first session. Thank you.
Monty?
Yes.
Cool. Ready?
Yes.
Okay.
All right. Hi, everyone. I'm Matti, and today I'm going to talk about our recent work on Gaussian belief space planning under temporal logic specifications. Well, in many real-world robotics scenarios, we don't have exact knowledge about the state of the system due to ubiquitous motion and sensing uncertainties. Take, for example, this drone, which is localizing itself using noisy radio signals from an antenna station. So as a consequence, we can only obtain a probability distribution over possible states, which is commonly known as the belief. And in many robotic applications, however, people decouple estimation and planning by doing state-space planning based on the most likely state, which can lead to catastrophic failure, as shown here, where we can have a high probability of collision. Instead, we focus on planning in belief space, which makes it possible to obtain paths that actively reason about the uncertainty of the system. And as opposed to other belief space planning frameworks, we want to solve problems under various spatial temporal specifications. And in our framework, it is possible to encode new desired system behavior, such as that we don't want to enter an area until our state uncertainty is sufficiently low. And our approach can be summarized as follows. Well, as follows. So we use Gaussian parameterizations of the underlying probability distributions and use the extended Kalman filter to model the belief dynamics. And then, given the belief, we define a specification in belief space using a fragment of risk signal temporal logic. And within this module, we propose a novel formulation of the risk of being inside or outside of convex polygon regions, where we leverage risk measures such as the value at risk. And the cool thing about using risk signal temporal logic is that it comes with the so-called robustness values. So we can quantify how well we satisfy or violate a given specification. And in the motion planning problem, we then maximize this robustness function subject to our belief dynamics to come up with a plan that satisfies our specification. And here we show now some preliminary results where we have a robot that is operating in a light dark domain. So here it can only accurately localize itself in the light areas, which could represent antenna stations. And then we have a specification given as a risk-aware reach avoid objective. And interestingly, we can observe this active information gathering behavior since the robot is always moving close to the antenna stations. And all in our work, we show that Gaussian belief space planning can be extended to solve complex, risk-aware spatial temporal tasks and thus go beyond the classic reach avoid. So thanks for your attention, and I hope to answer your question during the poster session.
Ready?
My name is Premchand and I am a PhD student at University of Delaware. And today I am presenting my work on interactive dynamic working, gate switching policies with generalization guarantees. First, I would like to thank my collaborators Sushant B and my advisor, Professor Yanis Polakakis. In this work, we consider the problem of a dynamically working bipedal robot adapting to the leader's intended trajectory, which is experiences from the physical interaction. Here we present the overall framework of our approach. In the high level, we see the supervisor, which takes the stride observations and maps them into a signal sigma k, which gives us the index for the gate controller that must be there during the next stride. Then at the low level, we have a feedback loop which executes the gates suggested by the supervisor. Here we see on the right the bipedal 3D bipedal robot with its coordinates. We model the walking as a sequence of alternating phases of single and double support, and the external force is denoted. In this slide, we explain the overall training pipeline. We generate a sample of environments, training environments from a distribution, and based on those distribution, we use the evolutionary strategies to train an inductive bias, which provides a prior to the model. Then we sample different training environments which are from same distribution, but they are sampled identically and independently distributed, meaning IID, to test the model. In this slide, we explain the results of the robot trying to follow the leader's intention. So we see that the robot is capable of staying within a tight tube of 0.5 meters around it and successfully completes the task. Here are some results of our the policy that we learned, and we saw that on increasing number of environments. So, for example, if you want to interpret the backbench bounds that we obtained, the robot is able to, we can ensure with 99% probability that the robot will be successful in 91% of the trials. Thank you for your attention. For more questions, we can hang out at the poster session.
Just let me know when you're ready.
Okay.
Ready? Good?
Hello everyone, my name is Dario Mantegazza. Many emerging robotics applications involve autonomous robots in unknown environments. These robots include the functionality to detect hazards that are expected during the system design phase from sensing data. During deployment, unexpected events can become hazards if not detected in time. These hazards can be more costly than aborting a mission early. We classify anomalies for robot along 4 axes. The first differentiates low-level sensory anomalies to high-level semantic one. The second differentiates, indicates if an anomaly is an hazard to the robot or not. The third discriminates visual anomalies that are geometric in nature from those that are not. And the last one, not shown in figure, indicates if an anomaly is relative to the robot or mission or not. We propose a novel dataset composed of 3 scenarios. The first one, called tunnel, is a simulation of a drone flying inside an aqueduct tunnel. The anomalies are water condensation on the ceiling, roots from the ceiling, and dust in the air. The second one, called factory, is a recording of a real drone flying inside an industrial building. The anomalies here are signal intake and mist from a smoke machine. The third one, called order, is a set of recordings of a ground robot that traverse a maintenance corridors of a university campus. Here we have recorded 8 different kinds of anomalies. And in all scenarios, all of them, the expected normal situation is an empty environment, while any object, person, or situation that differ from that is considered as anomalous. We then train using these models, this data, sorry, a model based on autoencoder and real MVP, and we then deployed it on a real drone. We show 3 videos. In all of them, on the top left, you see an image coming from the drone. On the center, the autoencoder's reproduction, and on the right side, an error map between the input and output of the autoencoder that highlights an anomaly. In the first video, we see no anomalies, so the system doesn't trigger the anomaly detection. In the second one, the drone is manually piloted and encounter the missed anomaly. Since it's manually piloted, the anomaly is detected, but then the pilot make the drone traverse the anomaly. And yes. Yes, the plot on the bottom side is the anomaly score that we are using to trigger the anomaly detection. And the last one, the drone is autonomous, the system is on board, and we detect successfully the signal intake anomaly. And in this case, we do not limit to detection, we also trigger a safety policy where the drone with tracks and actually makes also the second run that follows safe. Okay, we considered the task of detecting anomalies for autonomous mobile robots, categorized the relevant type of visual anomalies. We proposed a novel dataset to be built for this task, and we tested the state-of-the-art approach in real time. These are only the first steps of a larger project. Thank you for listening. Feel free to ask me any question here or at the poster session.
All right, ready?
Hi, everybody. I'm David, and this is our work on credible online dynamics learning for UAVs. So UAVs, and specifically hybrid UAVs, which combine rotary and fixed in flight, typically feature highly nonlinear dynamics, which makes accurate modeling a hard task. And ideally, therefore, you would like to learn or calibrate a model from the flight data. However, this is a safety-critical task because you have to apply the platform without the good model beforehand. So ideally, methodology to safely learn models from flight data will give us credibility. So an accurate model uncertainty quantification and we can use for safe planning. Be sample efficient because we cannot fly forever, and also run in real time and ultimately achieve good accuracy for high performance model-based control. So in this work, we try and address these four requirements by using the first principle-based nominal model, which provides speech generalization, combine it with a sparse pseudo-input GP in order to capture unmodeled effects. Then times with the fixed size and parameterized form of the sparse GP, we can combine these two models in a fully parametric dynamics model and estimate the parameters together with the state of the system using Bayesian inference on the state space model. So in order to achieve real time, in that case, we use filtering as an Bayesian inference method. So we then ask whether this residual learning actually helps to improve accuracy and credibility in presence of unmodeled dynamics, in a case which is very likely to experience on the real platform. So we test this on the simulated task of learning the longitudinal dynamics of a fixed-wing aircraft from typical onboard sensor data. Setup is as follows. So we have, for the simulated or ground truth system, a nominal parameterized model where we add a somewhat randomized pitch moment in order to emulate an unmodeled component. On the learning side, then, we try and learn the same nominal dynamics model and at the same time approximate this additional pitch moment using the GP. See whether residual learning helps in that case and to what degree. We compare it to the case where we ignore the additional pitch moment and only try and learn the nominal dynamics. In terms of the result, we see that learning rate for first is highly dependent on the information content of the trajectory, which would be to be expected. So for the gliding flight, which is basically steady state, there's not much to learn and the air stays somehow high, whereas for the highly informative drop trajectory, the air is quickly reduced over full state space. Now, whether or not we learn the residual actually doesn't make a big difference for that case. However, on the right side, if you have a look at the similarity between estimated and actual error distributions, you see that learning the residual in this case helps to improve the accuracy on the uncertainty specification. Also, from a safety perspective, we would like to have a low inclination index, which means that the predicted distribution should be a little bit wider than the true error distribution, which is for one the case, and for all, we see that at least including the residual learning gives us a lower credibility index, which is beneficial for safety. So thanks for your attention and happy to speak more in the poster session.
Ready?
Right. Hi, everyone. My name is Asta Acharya, here to talk about uncertainty quantification for competency assessment of autonomous agents. So for real-world deployment of autonomous agents, establishing appropriate levels of trust is of utmost importance. And one way to do this is to have the robot communicate its own competency by stating its confidence in completing the task. Our approach to competency assessment relies on having accurate long horizon forecasting of trajectories and task outcomes. So for example, in this poster robot task, the task is to get the ball to the target location in 30 seconds. We state the competency report from the forecasted trajectories, which then also tells us if the outcome is failed or successful. So for accurate long horizon forecasting of complex systems, we need proper uncertainty quantification of both aleatoric and epistemic uncertainties. Aleatoric uncertainty arises from the data due to processor measurement noise, any unobserved variables or intrinsic randomness, whereas epistemic arises from the model due to insufficient training data, outer distribution testing, or modeling errors. So for aleatoric uncertainty quantification, we use generative model in the form of conditional recurrent VAE. So the parameters of the model are denoted using theta, and we ultimately get the distribution of all future states given only the current state and an action sequence. And then for epistemic uncertainty, we train an ensemble of recurrent VAEs, which gives us a posterior distribution over the model parameters. So given this, the total uncertainty can be represented by just taking the entropy of the ensemble distribution, which is shown in 1. We can also look at the uncertainty of each of the individual models, which is shown in equation 2. And so the expectation of the model uncertainty under the posterior distribution of the learned model parameters is what gives us the aleatoric uncertainty. And then any remaining uncertainty not quantified as aleatoric is the epistemic uncertainty, which is shown in 4 there. So we can apply this to the pusher robot under deterministic, stochastic, and outer distribution environmental conditions. First, we can analyze the uncertainty entropy values over time for different states, such as for the on position, which is shown here. And here we see that epistemic is highest for the outer distribution and aleatoric is highest for the stochastic condition, which is expected. We can also look at total uncertainty for all time and for all states in the 3 conditions. And here we also present the competency values as forecasted probability of success. These allows us to see how the different uncertainty types correspond to the competency values. And we can say in this task, the agent is least confident in the stochastic condition. So in conclusion, this shows, I just showed how proper uncertainty quantification methods can lead to more informative competency reporting. For future work, we want to analyze how the different uncertainty types correspond with each other and interact with each other, and how that also impacts the agent competency. Thank you.
Not sure if anyone's coming in person for this one. So let's assume that they're not.
Hello everyone, we are glad to present our work, Effect Learning for Machine Perception with System-Level Objectives. First, let me introduce some background of our work. So the typical autonomous system consists of 2 components, perception and controller. Usually the controller contains the machine learning model as the true environment and output the perceived environment to the controller. Then the controller will make corresponding decisions based on these information. However, the perception component is often designed to be isolation from the control component. Also, the common loss functions fail to take into account the difference in severity of the system level failures due to different misclassifications. More specifically, for safety consideration, it is necessary to incorporate safety rules into autonomous system. For some specific class, for example, the pedestrian needs to have higher priority than other classes. Also, current perception components still have difficulty to formally specify properties that reflect human level perception. Last but not least, the widely used loss functions do not have the ability to represent safety rules. To resolve these limitations, I will let my partner Steve to introduce our proposed framework.
Thank you, Wesley. So hello everyone, I'm Sinyoung. I'll continue with the next part of the presentation, the proposed framework in our group. So the core of the framework is emphasized in the black box in the middle, where we still have the perception component and also the control component. But on top of that, we also have the rule book that Wesley had mentioned earlier in the introduction, and followed by the loss function that we'll use to update the model. So just to give the framework a little more context, we are experimenting this framework in an autonomous driving setting. So in the perception model, we are mainly doing object detection. And for the controller, we will look at the vehicle information such as position, velocity, and we'll perform actions that controls the car acceleration, steering, etc. Now that we know the entire setup, I will dive a little deeper into the loss and rulebook components. So in the loss function, we mainly have 2 parts. So first, we have the classical perception loss, so which are commonly the combination of a bounding box loss and a classification loss. Secondly, we have the rulebook loss as well. Taking one of the safety rules that we have in our rule, for example, the vehicle collision. So the function takes in an argument such as the action from the controller, the distances, and the vehicle state from the self-argument. and it returns the degree of violation of this rule as a non-negative value. Now we have a bunch of this rule in the rulebook. So what we get in the end is a vector with non-negative rule numbers. So using this violation vector, the rulebook loss can be computed as a weighted mean square error loss as expressed in the slide. So the weight in this equation is a rule weight that we assign based on the severity of the consequences if the rule is violated. So with that, I would like to thank you for your attention and feel free to reach out to us if you have any questions. Thank you.
This next talk is going to just be remote.
Hello everyone, I'm Sudarshan Saritas, a master's student at the Robotic Research Center in Tripoli, Hyderabad. I'm here to present my work, CCO voxel, a chance constraint optimization or uncertain voxel grid representation for safe trajectory planning. This work has been carried out along with my colleagues, Rishabh Del Yadav, Deepak Singh, Professor Arun Kumar Singh, and Professor K. Madhavakrishna. In an uncertain voxel grid representation, it is difficult to extract accurate distance to closed obstacle measurement, and furthermore, the gradients obtained are not stable. This might lead the trajectory optimizer to generate trajectories that go very close to obstacle or even can collide with it. Therefore, there is a requirement to develop motion planning frameworks that are agnostic to the underlying uncertainty in the voxel grid representation. As a solution to the defined problem, we propose CCO voxel, a method that accounts for the uncertainty in the distance to closure measurements and determines an optimal solution through a gradient-free cross-entropy minimization technique. An overview of our pipeline is as follows. The planning algorithm is initialized by the availability of a goal point. Pose and point cloud data is used to generate an optomap, and EDT is used to compute the collision distance for all the points in the map. Our initial trajectory search builds on the kinodynamic K-star, with the crucial difference that we use MMT as a part of the edge cost that connect the two nodes of the graph. Output of the kinodynamic K-star can be a suboptimal trajectory. We use cross-entropy minimization, a gradient-free optimization method, to further refine the trajectory, improve its smoothness, and maintain clearance from an obstacle. The MMT computation involves two steps. First, for a given query point, the collision distance is determined using EDT, and a non-parametric collision distance noise model is used to obtain multiple samples of the distance measurements and the corresponding constraint violations. An autoencoder is used to improve sample complexity and reduce computational load. For a given high-dimensional sample data, the autoencoder projects it into a low-dimensional embedding space, and the autoencoder is trained using supervised learning. In this paper, we further prove that the desired distribution can be modeled as a Dirac function to compute the MMT. The output of the cross-entropy minimization is an optimal trajectory. Simulations have been conducted for both qualitative and quantitative evaluation of our algorithm. We create two customized gazebo environments, namely the boxing in the world and the wall-grid world. Here we demonstrate the advantage of CCO voxel over a deterministic method. It can be observed that CCO voxel can avoid the obstacle, whereas the competing baseline collides. We conduct a fully autonomous test flight in an outdoor unknown environment. We use a customized self-developed quadrotor with a D415 camera, a Pixar flight controller with PX4 firmware. All the computations that include mapping, state estimation, and planning are conducted on an onboard Intel NUC. Please visit our project page for the code and further details. Thank you for listening.
Ready?
All right. Yeah, so today I'm going to be presenting a high level on our work titled Backward Reachability for Neural Feedback Loops, which is a work done at MIT by myself, Nicholas Robert, Michael Everett, and Jonathan Howe. This work is motivated by the need to develop certificates for neural feedback loops, which we consider to be closed loop systems with learning control policies specified by feed-forward neural networks. Previous work in this domain focused on forward reachability analysis to accomplish the goal of safety certification. Forward reachability analysis is a technique where an initial set of states is propagated forward to determine the set of possible future states contained by the reachable sets. Safety can then be certified by checking these reachable sets against dangerous regions in the state space, such as an obstacle. The problem with this strategy is that in some situations it can be overly conservative. In this example, we have two safe regions going around an obstacle. However, forward reachability analysis will label the situation as unsafe
because the reachable sets have to span both trajectories and thus intercept the obstacle. Our work approaches safety verification in a slightly different way, where forward reachability asks the question, where can your system go given a set of possible initial conditions? Backward reachability asks the question, where can your system have come from given a set of possible finite conditions, which we call the target set. Safety can then be verified using this approach by bounding an obstacle or other avoid region with the target set and checking what set of states leads the obstacle, which we call the back projection sets. As long as the system's state doesn't overlap with any of the back projection sets, we can guarantee that the system will not collide with the obstacle. While this has been studied for systems without neural components, the presence of a neural network makes this problem difficult because neural networks are generally non-invertible, making it hard to determine a set of outputs given this, or a set of inputs given a set of possible outputs. Our work circumvents the problem of propagating sets backward through a neural network by first finding the set of possible states that the system could have come from given limits on the control values. We call this set of states the back reachable set. Next, we relax the neural network over the back reachable set to get affine upper and lower bounds on the control values. These affine bounds give us a better picture of what the neural network is doing when compared with the saturation limits of the system. Finally, we use these affine bounds to determine the set of states that reach the target set while also satisfying these bounds, which gives us an idea of what the system could have actually come from, i.e. the back projection sets. We use this technique to show that we can certify safety for systems where forward reachability fails, like the situation you can see here. For any other questions or further discussion, please see my poster presentation or check out our paper. Thank you.
Hello everyone, my name is Brian and I will introduce you to the Explicit Reference Governance Framework, in short ERG, which can be used to efficiently provide safety for robotic applications. So the ERG is a robust closed form add-on scheme to make pre-stabilized nonlinear systems provably safe. And it does this by manipulating the reference velocity, V dot, via a dynamic safety margin and a navigation field, so that the transient dynamics are safe for any reference R of t. And when this reference is kept constant, there will be convergence to some steady state permissible state. So the first building block is the navigation field, which identifies the direction. So it's a vector along a path of strictly feasible equilibria. It brings the current reference V to the desired reference R. So one can use waypoint or vector field methods, but know that these only provide safety guarantees for slowly moving kinematic agents, so single integrated dynamics. So that's why we have a second building block, the dynamic safety margin, which predicts a minimal distance metric from a trajectory or a set to constraint violation. So the larger this dynamic safety margin, the safer it is to change the auxiliary reference. There exist different types of dynamic safety margins. Some are more performant, like the trajectory-based one. Some are more easy to robustify, like the Lyapunov-based one or the set-based ones. And some are used for like black box systems, like returnability-based. Here is an example of a double integrated system, and we see the phase plane plot with 3 invariant sets that touch the constraint, in this case a total trust constraint. So by solving some small nonlinear problems offline, we can basically align these level sets with the constraint in order to increase performance, or even compute a more generic, larger invariant set by finding that green point where the system dynamics stop pointing inward. So the larger the set, the better the performance, as can be seen in the step response, where it is almost twice as fast if we don't align it. Here is an example in a human-robot coexistence scenario where the human operator is trying to coexist safely with the robot, but while keeping the performance high, which is definitely not the case in most of the prior works. So here we show that the human can reposition an object safely, while the robot is accounting for both torque and effector speed and velocity constraints, and also joint angle limits. So this allows safe and performant operation in robot tasks. Finally, we also developed distributed ERG schemes, which we studied here for increasingly many UAVs to check how scalable they are. And we have seen that they are very scalable. And here we also compare the compute time versus the performance of these schemes. Moreover, we have also compared it with priority-based distributed predictive control schemes, which are of course optimization-based, and the performance is it's outperforming for like medium to larger swarms Of course, for smaller swarms, it will not outperform. If you want to visit the poster, feel free.
Ready?
Hello everyone, my name is Anil. Today I'm going to talk about our work input to state safety with disturbance observer based on control player functions. In this work, we consider the safety in the context of forward invariance, where we want our system trajectories to remain in a predefined set. We know that the control barrier functions give us a set of controller that actually ensures this task. We actually implemented this method for autonomous vehicle problem, but we are using this very simple double integrator model to control a truck, and we just want to be stay away from the leader from that critical distance away. So we actually implemented, as I said, this approach for the truck for a flat road case, and we were able to ensure the safety. However, the problem is if we have some external disturbances such as the road slope here, we realize that's actually no longer the case, unfortunately. If we take the like the worst case of the road disturbance, then it's going to be a very, very conservative result. So in that case, we just want to basically observe the effect of the uncertainty on the CDF online, and we just want to cancel that. So this is the our method. We have an assumption of this observer, this uncertainty to be upper bounded, the time this derivative of this uncertainty to be upper bounded. We are just making use of the term B being scalar, and we are actually coming up with this high gain disturbance observer, and we are actually observing that term B, and we're just canceling out that. We have two types of errors coming from the observer dynamics, and we actually use an input to state safety to handle the permanent error that is going to be the case as the time goes to infinity. In the input to state safety, we are actually coming up with a larger set to be the safe. We are kind of bounding the safety degradation in the system in the context of external disturbance. It is good because we can actually make sure that this larger set can be arbitrarily made closer to the original set by choosing appropriate parameters. When we implemented this method to the simulation, we saw that we can actually get safety without really following the leader not conservatively. And the simulation results here can actually show you that our ensured safety with the C bar is actually very close to the original safety task. Thank you for listening. I'll be happy to answer your questions in the poster.
Ready? Cool.
Hi everyone, my name is Wang Yu from the University area. This is a work of collaboration with Dr. Somarakis and Professor Adamoki. So today I'm going to present our work of original risk of cascading collisions in our platform of autonomous cars. So let us imagine on the highway there is a platform of cars, and our goal is aim to form a platform. And imagine yourself you're driving on the highway and you can see your car in the front and car in your back. And this is actually the communication of that path graph. And we also assume there exists the time delay and the equivalent sentences. So for the time delay, you can imagine that as a human, we always take some time to react to something that we haven't seen before, which is for example, by accident. And the other thing is that when we are driving, actually our feet putting in the pedal is actually shaking all the time. So as a result, by solving these dynamic systems, we can solve that the intervehicle distance is actually a random variable, and we consider the failure as a collision, which is whenever it's less than 0. So given the fact that as a random variable, the chance of this kind of event eventually happening is going to be 1, which is almost surely. And we consider the risk of cascading collisions, which is whenever there already exist collisions or failures in the system. And by doing that, we can see that we can form the value risk measure. by taking the conditional probability distribution of the theoretical distances, and we can form our simulations on the one side. Let's take a look at this simple blue curve at first, which is the risk of single collision, which is no periodic collisions. And you can see that in the past graph, the vehicle that in the middle has the most risk to have collision. And on the graph which is next to that, that is the cascading collision in the past graph. You can see that it shows a very different profile and based on the locations of the previous collisions, and it shows different properties. And you can see the 3D bar plots, those are the cases whenever there's more than one existing collisions in the system. And you can see that based on the spatial distribution and total number of existing collisions, they show different properties. And we also observe some very interesting trade-offs between the single collision and the graph connectivity, which is that the product of these two numbers are actually lower bounded by a positive real value. And also the single collision risk and cascade collision risk, which is showing that you cannot arbitrarily minimize both of them at the same time, and you need to take a trade-off and decide which one you want to minimize most. And as a concluding remark, I would like to give some exclusive safe driving tips to everyone. So which is that, first of all, please keep this safe distances, which is minimizing the probability of having a collision, and also stay focused, which is minimizing time delay. And in the end is to try to balance the information you receive from the recent cars and the car that's far away. So thank you so much for your attention, and I'm happy to see you at the further sessions. Thank you.
All right, our next two talks are going to be remote, but they are actually here for the poster session.
Welcome to this short lightning talk on safe real transfer for high-speed photonic flights. I'm Pierre Kaufman. I'm a PhD student at the Robotics and Perception Group in Sterling. Today I will speak about vision-based agile flight with quadrupers. Quadrupers have a very limited bandwidth, which constrains their range. So if you want to maximize the utility of quadrupers, we need to make the flight fast such that they can achieve more mission on the same battery charge. There are many applications that benefit from such more capable drones, such as search and rescue scenarios, delivery, or exploration. However, pushing an autonomous drone to higher speed raises fundamental challenges in robotics, ranging from perception or climate control. In my research, I investigate learning-based entry model policies. In contrast to traditional approaches to vision-based autonomous flight, learning-based entry model policies directly map from onboard observations such as visual observations such as feature tracks, eye movements, or a reference trajectory to control commands. Such direct mapping and therefore tight coupling allows to achieve low latency perception to action. As such data-driven approaches require a lot of data to be trained. They are typically trained in simulation. Simulation is a perfect training ground for such a task because it's fast, cheap, and safe, and it provides full information about the environment and doesn't require any human adaptation. However, training such a learning-based policy in simulation requires to bridge the simulation to reality. In my research, I showed that suitable intermediate representations benefit the simulation. Specifically, I showed that abstraction of sensory observations reduces the relationship between simulation and the real world. I also showed that we can use abstraction of the control modality of the policy to benefit simulation. I demonstrate this idea on the task of vision-based acrobatic flight, where we show the first quadruped can perform such acrobatic maneuvers completely vision-based and with only onboard computation, as well as on the task of high-speed flight in the wild, where we demonstrate that such a learning-based sentry model policy can achieve high-speed flight at up to 10 meters per second in previously unseen cluttered environments, ranging from dense forests to snowy mountain trails and disaster scenarios. If you think that sounds interesting, check out our webpage, speak to me after the poster session, or drop me. Thanks a lot.
And this one's also going to be remote.
Hello, my name is Drew Hanover, and I'm a PhD researcher with the Robotics and Perception Group at the University of Zurich. Today, I'm presenting my recent work on adaptive nonlinear NPC for quad rotors in uncertain environments. For any sort of model-based controller, typically we require an accurate model of the dynamic system to achieve satisfactory control performance. When the system is complex and nonlinear, as is the case for high-speed quad rotors, these models become increasingly difficult to procure, often requiring high amounts of domain expertise or data. Once you've learned the model, it won't generalize to changes to the platform. For example, unknown payloads, rotor failure, changing aerodynamics, etc. It begs the question, how can you control a system that you know very little about? For example, in the video on the top right, we see a quad rotor flying with an unknown payload of 450 grams, or in the bottom right, taking off with an unknown beer payload attached. Our approach was first to leverage our knowledge of the known properties of the quad rotor system by building a first principles-based model, and then using this model inside a nonlinear NPC. Next, we used the solution of the NPC to derive the desired dynamics to track a reference trajectory and feed these dynamics into an L1 adaptive controller, which uses our nonlinear quad rotor model as the reference dynamics of the system. Over time, we drive the plant towards the desired dynamics from the NPC, using the differences between our model prediction and the measured states of the quad rotor. With this setup, we avoid needing to acquire a data-driven model to learn unmodeled dynamics from the first principles approach. And it also enables us to be resilient to model mismatch, such as mass, inertia, and aerodynamics. We demonstrate the efficacy of this approach on a series of real-world experiments using a racing quad rotor. All of the controls are computed onboard the quad rotor in real time. And across each of these scenarios, neither the underlying model nor the controller gains are modified. In scenario 1, as seen in the top left, we demonstrate a 70% reduction in RMSE on increasing speed circle trajectories versus a recent Gaussian process-based nonlinear NPC. We did not even need an aerodynamic model embedded in the NPC. Next, in scenario 2, unknown to the NPC or the L1 controller ahead of time, we attach a 450 gram payload representing a 60% increase in mass. Adaptation occurs immediately, resulting in less than 1 centimeter RMSE. And similarly, we can introduce an aerodynamic disturbance in the form of a fan that the adaptive controller has to immediately compensate for. Next, in scenarios 4 and 5, we can attach unknown payloads that are slung. This is a 100 gram payload that's unknown to the NPC, and we can demonstrate even better tracking performance compared to a non-adaptive NPC without a payload attached. And again, with the same controller, we can fly a highly aggressive racing trajectory with top speeds of over 20 meters per second and 4 G's linear acceleration.
Okay. Good.
Hello, everyone. My name is Bill Bexey, and I'll be presenting our work on evaluating uncertainty calibration for open set recognition. The goal of this work is to evaluate calibration techniques under open set conditions for the first time. So what is calibration? Calibration of deep neural networks refers to obtaining predictive probabilities that reflect the true correctness likelihood. And it's very important, extremely important for safety critical applications such as robotics and self-driving cars, where having reliable predictions is key. So traditional evaluations are simply either for closed set data, or they have no explicit rejection option for data that's coming from unknown classes or classes that you did not train on. What is open set recognition? So open set recognition identifies instances that are not from any of the training classes while trying to maintain a discriminative capability of the closed set classification. Okay, and so we do this by adding an additional none of the above class for rejecting those unknown samples that we come across. Okay, so inspired by or motivated by this novel problem, We evaluate using these classifiers, so ResNet, DenseNet, and EfficientNet on these two different data sets, SVHN and the CFAR10. And so we randomly split the data into known and unknown classes. And then we do two of the following things. First, we obtain a threshold on the model that we learned based on a redistributed predicted probability distributions. This serves as our baseline. We also apply a very well-known technique for OpenSet classification called OpenMax. We use that for comparison. And then we use a very popular technique called temperature scaling for doing the calibration. And here we can see the results of ResNet on the CFAR10 data set. So on the left, we see the reliability diagrams, which allow us to visualize the calibration performance. And then on the right, we see a table that shows the Breyer scores and the effective calibration error. And so the key takeaway here is that temperature scaling is only effective to a small extent on OpenSet recognition. And thus we argue that there's a need for developing new techniques that can provide OpenSet recognition for safe and reliable autonomous systems. For more information, please visit our poster. Thank you.
Hello everyone, I'm Kunal Narkere. Today I'll be presenting our work on reactive motion planning based on sequential model predictive control for bipedal robots. Our approach is based on RRT guided decomposition of the free space into sequentially intersecting polygons, which are then incorporated into the model predictive control framework as control barrier function constraints. The footstep pattern generated by the sequential MPC is tracked on the robot using operational space control formulated as a quadratic program. First, the available free space is partitioned into obstacle-free polytopes and the corresponding intermediate waypoints. Our algorithm ensures that the resulting polytopes are sequentially pairwise intersecting and the waypoints are located within the intersection of the polytopes. The polytopes and the waypoints are used to define a sequence of MPC programs that drives the system from to the goal location while ensuring that the evolution is kept within the obstacle-free polytopes. The sequential MPC employs the linear inverted pendulum model to generate the footstep plan. The cost of each MPC is designed so that it transfers the system from current polytope to the next to the intersectional area. As soon as the system enters the intersection area, the algorithm switches to the MPC next in sequence. Finally, the polytope, the footstep plan generated by the MPC is tracked on the robot using operational space control formulated as a quadratic program. We implemented the proposed sequential MPC and QP-based operational space control to plan and execute obstacle-free motions in hyperfield simulations on the bipedal robot digit. We used Mojoko as our simulation environment. In this scenario, we show how digit avoids collision on both static as well as moving obstacles while traversing a reference polytope plan. Finally, we tested the robustness of our method to unknown external forces applied to the digit's torso. The applied forces are drawn at random from a uniform distribution with a maximum magnitude reaching up to 80 newtons. This figure shows the center of mass trajectories for digit for 29 out of 30 successful trials of traversing an obstacle course in presence of randomly applied unknown external forces. Owing to the ability to solve the sequence of MPCs at sufficiently high frequencies, the robot was able to maintain balance and complete the objective of reaching the goal without collisions, keeping the center of mass within the union of polydopes. The presented results demonstrate that our method is capable of performing online reactive planning on a complex bipedal robot like digit in uncertain and dynamic environments. Thank you. I'll be happy to answer questions during the poster sessions.
Almost there. Okay. All right. Ready? Let's do it.
Hi, I'm Catherine Shea, and I'll be presenting on safety and indoor navigation for guide robots. So we can use robotic guides to provide physical navigation assistance, particularly for people who are blind or low vision. And these guides that are available in public spaces, such as transit stations, could improve accessibility by allowing easier travel through these complex dynamic scenes. But when escorting their users, they must be able to navigate to their goals both safely and efficiently. So to study the features and utility of robotic guides, we use a small mobile robot with a handle for the user to hold onto. We assume the user doesn't have any special equipment to interact with the robot. The robot has a forward-facing LiDAR with a limited field of view. And to avoid any discomfort or injury to the user, it does not back up, so it can only move forward or turn. Although the user's position behind the robot is constrained by their grasp on the handle, this still allows for a wide range of relative poses. So simply planning robot paths as if the user might be in any part of that possible space is excessively conservative. To provide reactive safe controls that interface readily with higher level planners, we're exploring a control barrier function based method that governs rotational motion. Our model of user position, which was proposed by Nanavati et al., updates the user's pose based on an average of the position directly behind the robot and the closest position in a region of occupancy defined by an annular segment. However, this model is non-differentiable. We can't use it directly. So we pre-compute a system pole drawn around the XY point coordinates in 2D space of the robot and user. The exact shape of this pole also depends on the initial position of the user and the change in rotation of the robot, so it is four-dimensional. So to construct a safety index with which to define a control barrier function, we retain a set of nearby LiDAR points, including those that pass into the unsensed region behind the robot, all within the swaying radius of the robot. During each control loop, we are comparing the pre-computed pole against these points to find the maximum and minimum angle of rotation the robot can achieve without a collision. We are fitting a symmetric one-dimensional quadratic function to this point, use that as our safety index. And as in other CBA-based methods, we're solving for the nearest to nominal robot control that keeps the safety index greater than 0. We conducted some preliminary simulations using this method on a robot and user traveling through a building. We tested the system under both nominal and CBF-enabled control for several representative paths and found that the CBF-enabled system had some minor improvements in safety, but took approximately 10 seconds longer per path to complete. And the safe control tended to intervene mostly near doorways where it was constraining the robot to move in straighter paths. We plan to continue exploring methods of improving safety in robotic guide systems, particularly those that address under-actuation, imperfect sensing, and the problem of predicting the user's actions. We also plan to explore definitions of user safety that are not simply obstacle avoidance, such as comfort, path legibility, and memorability. Thanks so much. I'd love to chat about in poster sessions.
All right, ready?
Good afternoon. Can we allow humans to supervise autonomous vehicles in dangerous driving situations such that we can do better in a scalable way, such that we can do better than have one human supervise one vehicle at all times? If you've ever watched a Roomba, that's not a very fun situation. So we propose, or our work makes two contributions. The first is that we extend theoretical results to real-world supervision in real-world supervision scenarios that are modeled with realistic traffic parameters, so that we can identify trends and gains as a function of AV penetration rate, and then we learn cooperative AV strategies via RL to show empirical supervision gains. Obviously, we're all familiar with here the benefits of autonomous vehicles, but also their danger, their problems. But the work here is notable in that it's applicable, or it's focused on AVs, but it's applicable to a wide range of autonomous and semi-autonomous settings beyond AVs. So we're focused on a highway merge scenario, and we can see the simulated traffic network here. Basically, we have 4 merging roadways into a ring road, which is known to approximate an infinite highway. And we impose a fully conservative safety requirement such that anytime an merging AV can collide with an in-ring AV, we require that a human supervisor supervise that situation. We have that equation there, which actually shows the kind of the failure rate. That is cases where merging AVs would attempt to merge onto the roadway, but not be able to get a supervision when they require. So it's kind of a bad equation that we're afraid of. And we use that to plot some theoretical results in terms of what we expect supervision requirements to be in real world settings. And so this is using realistic traffic and inflow rates. We're interested in a human baseline, and then a non-cooperative connected AV case, and a cooperative connected AV case. While in the human case, you would expect supervision requirements to scale linearly with AV penetration rates, we actually see that the relationship is non-monotonic for the connected AV case and actually gets better with higher penetration rates. Here's empirical results, which I'm happy to discuss more at my poster and invite you to come over. Basically, the TLDR here is that connected cooperative AVs with policies learned via reinforcement learning can learn teaming behaviors such that in high traffic or in light traffic, top row, and lower and heavy traffic, bottom row scenarios, we actually see the agents are able to learn behaviors that decrease scaling requirements while still allowing decent system performance overall. Looking forward to talking about the poster. Thanks very much.
All right, and this is our last contributor talk. Ready?
Hello everyone, my name is Andrea Tagliabue and today I'm presenting work done in collaboration with Professor Jonathan Allen. The objective of our work is to reduce the computational cost of computationally expensive model-based sensing and control algorithms such as MPC and visual odometry. We do so by training a neural network visuomotor policy with small inference time. This policy should be capable to control a mobile robot by directly using images and data noisy sensor measurements. One of the leading approaches to train such a neural network visuomotor policy is to use imitation learning. However, imitation learning techniques are usually affected by the effects of process and sensing uncertainties, as they can cause shifts between the training and testing distribution, resulting in policies with limited robustness. Additionally, these methods require a large number of demonstration and long training time, requiring expensive training equipment and making it impractical to collect data on the real robot. But is it possible to generate a robust visuomotor policy in a data and computationally efficient way? We answer positively to this question by using an approach that derives from collecting demonstrations from an output feedback tube MPC, which is a controller robust to the effects of process and sensing uncertainties. The key idea of this method is to use a tube centered around a nominal trajectory to describe the set of state, the possible state perturbation due to sensing and process uncertainty. The effects of these uncertainties are captured in the width or cross-section of the tube. Additionally, tube MPC employs an auxiliary feedback controller called ancillary controller, which can compensate for the effects of these uncertainties, and you can see at the bottom of that figure. Our overall idea is twofold. First, we collect demonstration using existing output feedback tube MPC methods. Second, we use properties of the tube to derive a data augmentation strategy, which can be combined with demonstrations collected by existing imitation learning methods. Specifically, we sample extra states from within the tube, and we use a 3D reconstruction of the environment, which is in the back of the picture, and a model of the sensor on the robot to generate corresponding extra images, which can be then used to augment the training data. Corresponding actions can be efficiently computed via the ancillary controller, which is again shown on the bottom. It's just a linear feedback loop. We numerically evaluate our method on the task of trajectory tracking for a quadrotor. The results show that our training approach produces a policy that is highly robust to the effects of process and sensing uncertainty, such as wind and noise, while requiring about 2 orders of magnitude less demonstrations than leading imitation learning methods. Our strategy additionally takes about half of the training time to achieve higher robustness to the effects of uncertainties. In the future, we would like to perform hardware experiments and robustify the policy with respect to small visual changes in the environment. To know more, please come visit our poster. Thank you.